In this video, we are going to talk about solving a special case of second order differential equations. We're going to talk about ones that are written in the form ay double prime plus by prime plus cy is equal to 0. And the goal is to try to find a solution of the form y equals e to the mx. So if we were to think about that being a possible solution for this second order differential equation, then let's just do some fancy math here. Let's do some substitution. So if we were to take that first derivative, we would get me to the mx. And then if we were to take the second derivative, we're going to get m squared e to the mx. So suppose we did a substitution. So we're going to have a times m squared e to the mx plus b times me to the mx plus c times e to the mx is equal to 0. Notice every term has that e to the mx in common, so we could factor it out. So the only way we could satisfy this equation is if this exponential function is equal to 0, or if am squared plus bm plus c is equal to 0. Well, we know there's never a place that exponential function is going to be equal to 0. So there's no solution that's going to come from that, which means the only way that we'll be able to satisfy this differential equation is if we were to solve that quadratic, where we have am squared plus bm plus c is equal to 0. So that's kind of the theory of what we're getting ready to do. So we know when we solve quadratics, you actually have three cases. And I'm thinking about that quadratic formula, because not every quadratic factors, but the quadratic formula will solve any quadratic. And what happened with the quadratic formula, let me write it out, really depends on what's going on under that square root. So there's three things that can happen under that square root. Either b squared minus 4ac, and that is called the discriminant, is going to be a positive number. If that's a positive, we know that we're going to have two distinct means different, real roots. Which means that, going back to this differential equation, we're going to have two solutions to the differential equation, and that's going to be in the exponential form that will satisfy this differential equation. We will know m values in this case. The other option, or another option, is that b squared minus 4ac is equal to 0. And if it's equal to 0, we're going to have one distinct root. Distinct means different. A lot of times we call that a double root. So graphically, what's going on there, if you were to graph that quadratic, is a quadratic would touch the x-axis at that particular root value. It would not cross the x-axis at that particular root value. And then the third option is that discriminant is a negative value. And in that case, we end up with complex roots. Remember, complex roots always come in pairs. So you're going to always have two of them. And they're going to be conjugates of each other. So one would be like a plus bi, the other one would be a minus bi. In the case of complex roots, we could use something called Euler's formula. So if we have a complex root for that m value, remember that's everything's going back to what we're assuming that solution would be, which would be exponential. Then that means we're going to have an I up here in that exponent. And we could rewrite that in terms of sines and cosines using Euler's formula. And Euler's formula says e to the I theta equals cosine of theta plus I sine of theta. So let's talk about what those general solutions are going to look like. We kind of made that assumption in the beginning that we're going to try to find a solution for this special case of a second order differential equation where it's equal to 0, so it's a homogeneous differential equation. We're assuming that form is going to be y equals e to the mx. So if we end up with that quadratic, I'm going to call this guy the auxiliary equation. And we were to solve that quadratic and we were to get two distinct real roots. We're asking what would that general solution look like? And that's where we're using that superposition principle from section 4.1. So if that discriminant is positive, we know we're going to have two distinct roots. They're going to be real. So I'm going to call them M1 and M2. So then our solution would be y equals some constant of integration C1 e to the M1x plus C2 e to the M2x. Those roots end up in the exponent. In that second case, where we ended up with that double root, and that happened because that discriminant is equal to 0. We know one solution is going to be e to the m1x. Our goal is to find y2. And we could think about that by using that reduction of order formula from that last section. So remember what the reduction of order says? I'm just going to use that formula that we talked about. This is how we would find that y2 value, and that's what we're looking for here. So let's think about first, what would that quadratic look like? Because we got to figure out what the p of x is going to be. If we have a double root, we're trying to answer what would the auxiliary equation look like. So we're doing some side work over here, if you will. So, well, if we have a double root, we know it can be written this way. We must have been able to factor that, if you will, as x minus that root quantity squared. And there could have been a coefficient that we would have pulled out in the beginning. I'm just going to put an arbitrary a there. And then if we were to multiply everything out, it would look like that. So if we think about what our p of x is, our p of x is going to be this guy. So we've got our y1, which we already said was e to the m1x, times the integral of e to the negative integral of p of x, which is negative 2m1, times dx, over that y1 quantity squared. So this is what our y2 is going to look like. Now let's simplify all of this fun stuff. When we integrate -2 and 1, that guy's just a number, and we integrate with respect to x, we're going to get -2m1x. Well, that negative times this negative here will end up being a positive, so that's going to be 2m1x. And then when we square that bottom, we're going to end up with a 2m1x in that exponent also. And notice that's going to reduce the 1. And then when we integrate 1, we're going to get x. So this is going to be x times e to the m1x. So there's our y2. So our general solution would be equal to c1 e to the m1x. So there's our y1. Plus our y2, which is x times e to the m1x. And then that third case, if we had a negative discriminant, so b squared minus 4ac was less than 0, we ended up with complex conjugates. So what that means is that our y1, write it over here, would be e to the, and I'm going to use Greek letters alpha and beta, alpha plus I beta times x, and then y2 would be e to the alpha minus I beta times x. So the general solution would be c1 e to the alpha plus I beta times x plus c2 e to the alpha minus I beta times x. But we will be able to apply Euler's formula to both of those exponential functions. So we could rewrite those this way. First, let's distribute that x term. So we're going to have alpha x, and then we're going to have e to the I beta x. So I'm undoing that addition in the exponents when you would combine those terms. So we're going to have e to the alpha x times e to the negative I beta x here. So notice both of these have an e to the alpha x in common. So we could factor that out. So now we have c1 e to the I beta x plus c2 e to the negative I beta x. And this is where we can apply Euler's here and here, since both of those have that exponential imaginary piece. So let's do that. So we could rewrite this as c1 times, this is going to be cosine of beta x plus I sine of beta x using Euler's formula. And then plus c2 times, and we're doing the same kind of thing here for this piece. It's going to be cosine of negative beta x plus I sine of negative beta x. And then we're going to use some trig properties to help us simplify that. So we have e to the alpha x times c1 cosine of beta x plus c1 I sine of beta x. and then we're going to have plus. And I'm going to think about distributing that C2 also. But let's think about properties of cosine and sine. We know cosine is an even function, which means cosine of negative beta is the same thing as cosine of positive beta. So this is going to become C2 cosine of beta x. We know sine is an odd function, which means sine of negative beta I is equal to negative sine of beta x. And if I distribute that, C2, I'm going to have that. So now let's think about combining like terms after we've used those sine properties and cosine properties of even odd functions. So I have a constant times cosine of beta x plus another constant times cosine of beta x. Isn't that the same thing as just some new constant times cosine of beta x? And then we could do the same kind of thing here. I have a constant minus a constant, which is going to give me another constant times I sine of beta x. So you can see how we can take that original formula and we can really simplify it, and using Euler's formula, turn everything into sines and cosines. So now that we've talked about all of the theory, let's put it to use. Let's do some applications. Let's solve some differential equations. So your first step is always to figure out what is that auxiliary equation. And remember where that auxiliary equation is coming from. It's coming from that idea that we can find a solution that's exponential, and finding those derivatives and plugging everything in. So then if we make this substitution, we're going to have m squared e to the mx minus 36y. So if we were to factor an e to the mx out, we're left with m squared minus 36, which is equal to 0. We know there's not going to be a place where that exponential is equal to 0, but there are places where m squared minus 36 is equal to 0. And those places are at positive and negative 6. So our first solution is going to be e to the 6x. And our second solution is going to be e to the negative 6x. Using that superposition principle, we can put those together to get that general solution. So there's our answer. Let's look at the next one. We have y double prime plus 4y prime minus y is equal to 0. So we're making the assumption the solution is in the form y equals e to the mx. So y prime is m e to the mx. And y double prime is m squared e to the mx. So if we were to make those substitutions, we could factor out an e to the mx. That's going to leave us with m squared plus 4m minus 1. Guys, this guy is called your auxiliary equation. So that's what you're going to try to solve. Remember, there's no place that this is going to be equal to 0. We're using that zero product property going way back to an algebra class. So this is what we're going to try to solve. That's your auxiliary equation. So if we want to solve that, we're going to have to use that quadratic formula. So the quadratic formula says it's going to be negative b plus or minus the square root of b squared minus 4 times a times c, and all of that's over 2a. So these roots are not going to be very nice. So 20 is the same thing as 4 times 5. So we have 4 plus or minus 2 square root of 5 all over 2. You should always simplify square roots. And that's the same thing as 2 plus or minus square root of 5. So we do have 2 roots. They are irrational roots. So then our solution, this is the general solution, is C1e to the negative 2 plus square root of 5x. And then C2e to the negative 2 minus square root of 5x. I do want you to notice those parentheses around those roots. Negative 2 minus square root of 5 has parentheses around it. And negative 2 plus square root of 5 has parentheses around it. All of that will be multiplied by that x. So those parentheses are important. So there's our general solution. Okay, let's do another one. So we're assuming we have a solution in the form y equals e to the mx. So y prime equals m e to the mx and y double prime equals m squared e to the mx. If we make that substitution, we're going to get 3m squared e to the mx plus e to the mx is equal to 0. And we could factor out e to the mx, leaving us with 3m squared plus 1. So we see we're going to have an imaginary root. They always come in pairs. So then our solution is going to look like this. C1 e to the I over square root of 3 times x plus C2 e to the I over negative I over square root of 3 times x. So this is where we want to use Euler's. And you always want to simplify as far as you can. Euler says e to the I theta equals cosine of theta plus I sine of theta. So if we replace e to the I over square root of 3x, we're going to have cosine of x over square root of 3 plus I sine of x over square root of 3. And then if we replace this e to the negative I over square root of 3x, we're going to have cosine of negative I over square root of 3. I'm just kidding, negative x over square root of 3. Plus I sine of negative x over square root of 3. And now you want to simplify that. So I'm going to do a couple things in one step here. I'm going to distribute that C1. And then I'm going to think about distributing that C2 and think about even odd properties. We know cosine is even. So cosine of negative x over square root of 3 is the same thing as cosine of positive x over square root of 3. We know sine is odd. So that's going to be equal to the negative of C2 times I times sine of x over 3, square root of 3. And then we want to combine like terms. We can put those cosines together. That's going to create a new constant. I'll call it C3. And then if we put the sine terms together, it's going to create a new constant called C4. And in fact, if we wanted to, we could say C3 and C4 are complex. C1 and C2. If we put those together into C4, we could say C4, let that C4 absorb that I, and say that C3 and C4 are actually elements of the complex numbers. And we know C4 would definitely be a complex number because it's got that I value absorbed into it. So we could even condense that just a little bit further by eliminating that I and saying these are elements of the complex. Remember, a complex number can be written in the form of A plus BI. Even real numbers are technically complex numbers because a real number like 3 could be written as 3 plus 0i. So that is definitely a true statement. Let's look at another example. And this is where you may want to pause the video, try it, and then come back. So if we look at this one, same process. This is a third degree, or third order, rather, differential equation. So, but the process is the same. We're still assuming we have something in the form of e to the mx. So y prime is m e to the mx. Y double prime is m squared e to the mx. And y triple prime is equal to m cubed e to the mx. And if we were to make those substitutions, we have m cubed e to the mx minus e to the mx is equal to 0. So we have e to the mx times m cubed minus 1 is equal to 0. So our auxiliary equation is m cubed minus 1 equals 0. This guy is a difference of cubes. So we have to use that difference of cubes formula. If you just set that equal to 0 and you solve it, you're going to get one root. All that tells you is you have one real root. You haven't found the imaginary roots. And you will have two imaginary roots because going back to 171 pre-cal algebra, there's got to be 3 roots to this equation. Setting this equal to 0, we can easily see that 1 is a root. The other 2, since we didn't get them algebraically, have to be complex roots. So to find the complex roots, we have to use the difference of cubes formula. And if you think back, difference of cubes formula, a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. So this guy's going to factor into m minus 1 times m squared plus m plus 1. So we know 1 is going to be a root. To solve this one, we're going to use that quadratic equation. Negative b plus or minus square root of b squared minus 4 times a times c all over 2a. So we're going to get negative 1 plus or minus the square root of negative 3 over 2, which is negative 1 plus or minus I squared root of 3 over 2. So right now, our solution, we have 3 solutions. We have y is equal to c1 e to the x plus c2 e to the negative 1 minus I squared root of 3 over 2 times x. And then c2 e to the negative 1 plus I squared root of 3 all over 2 times x. When you're writing these, make sure I can tell what your exponent is. So now we're going to have to use Euler's formula on these 2 pieces in order to simplify. And this guy's going to simplify quite a bit. So before I apply Euler's formula, I want to rewrite those exponents. So we're going to have e to the, this is negative x over 2 and then e to the negative ix square root of 3 over 2. So I'm separating that real and that imaginary component there. I'm going to do the same thing with the other one. This is e to the negative x over 2 times e to the I square root of 3 over 2x. Yeah, I think I'm going to put the x at the back here. So I'm going to do that same thing over here. So I have the number times x. It's easy to lose a piece in these. There's a lot of pieces. So notice I could factor an e to the negative x over 2 out. Oh, let me fix my constant here. Let's call this guy C3. Sorry about that. Just to make it clear, those are 3 different constants possibly. So I'm going to factor out that e to the negative x over 2. And that's going to leave us with C2 e to the negative I squared of 3 over 2x plus C3 e to the I squared of 3 over 2x. And now we can apply Euler's to both of those pieces. So we have C2 times, this is going to be cosine of root 3 over 2x, negative root 3 over 2x, plus I sine of negative root 3 over 2x, that's C2, plus C3 times cosine of root 3 over 2x, plus I sine of root 3 over 2x. So thinking once again about those even-odd properties, and I'm not going to write these out, but let's talk through it. So we can put those cosine terms together because I know the cosine of negative square root of 3 over 2 is the same thing as a cosine of positive square root of 3 over 2. So these two do have that same argument. So that would be combined so that we have, I'm going to call it C4, some constant, times cosine of square root of 3 over 2x. And then the same kind of argument for those sines. We put these two together. We know sine is an odd function. So this first term is the same thing as negative sine of square root of 3 over 2x. And a constant times that plus a constant times that other sine is going to be another constant times sine of square root of 3 over 2x. I am going to let this constant absorb those i's. And then we're going to say C1, C4, and C5 are elements of the complex numbers. So there is our final solution. So as you're going through these, guys, you're going to start seeing those patterns. The more you apply Euler's, the better you're going to get at them. And you'll eventually be able to go probably from here or even here down to this point where you'll be able to get there. So you'll be able to skip some of that middle work. I'm showing all of that now because we're just kind of getting our feet wet. Okay, let's do another one. So this is another third order. I want you to take a minute, pause the video, think about what that auxiliary equation is going to look like. Come back, tell me what it's going to be. So in this case, our auxiliary equation is going to be m cubed minus 6m squared plus 12m minus 8. And you're probably asking, how am I going to factor that? So this one, we're going to have to use that rational root theorem and remainder theorem going back to Math 171. So the rational root theorem will give you a list of possible rational roots. And what it says is that you're going to find something called P's and Q's. P's are always going to be the factors of the constant on the end when it's in standard form. So in this case, our constant is -8. We're asking what numbers can we multiply together to get 8? Or -8. Well, we can multiply 1s and 8s. Or we can multiply 2s and 4s. And we're thinking about all possible combinations. So it could be a +1 and a -8, or it could be a -1 and a +8. That's why we have the plus and minuses there. Q is going to be factors of the leading coefficient. In this case, our leading coefficient is 1, and we want all possible factors, so we're going to use that plus and minus again. If there is a rational root, it's guaranteed to be in the list of P's divided by Q's. So if I take every P value and I divide by every Q value, I have 1 divided by 1, which is 1. I have 2 divided by 1, which is 2. I have 4 divided by 1, which is 4. And then I have 8 divided by 1, which is 8. If we have a root, it's guaranteed to be in here. Now, we are hoping that all 3 roots will be in this list. So let's see. So this is where you're going to want to use your calculator. So I'm going to go to y equals, and I'm going to type in my function. And I'm just using the calculator just to do a lot of quick computations here. So I'm going to go to second and table. And I'm going to type in my values. Any value that gives me a 0 is going to be a root. So we can see 1 and -1 are not roots. And this is what the remainder theorem says, is that if you plug in a number, then it will tell you what the remainder would be if you're dividing by that number. So when we plug in 1, then if we were to divide this by x minus c, our c is 1, so x minus 1, then we would end up with a remainder of -1. Any remainder means we don't have a factor. So we're looking for remainders of 0. So 2 works. So we know x equals 2 is going to be a root. So you can see we only have one root that we know of, and that's that x equals 2. So we know that we plugged in 2, we got 0. So that means, and I'm going to use m instead of x, m equals 2 is a root. So m minus 2 is a factor of this cubic equation. So now let's do some synthetic division. So we have, for our auxiliary equation, m squared minus 6m plus 12, plus minus 6m squared plus 12m minus 8. We're going to divide it by x minus 2. So 2 goes in the box. The box is always the root. Bring down the first term, multiply, add down the columns. We're going to get 0 for the remainder. So this is x squared minus 4x plus 4. And we know this guy factors. That factors into x minus 2 times x minus 2. So then our cubic, I'm going back up to the top now. This guy is the same thing as m minus 2, which was that first factor we found, times m minus 2 times m minus 2. So this guy is actually what's called a triple root. So we got to think about how we're going to write that solution. Well, we know y1 is going to be x e to the 2x. And then if we think about all of that theory we did on that first page, we found y2 to be x times the root to the x. I miswrote this. This is just e to the 2x. So then if we were to think about doing the same thing over here, trying to find that y3, we would actually end up with an x squared times e to the 2x. So then our solution is going to be c1 e to the 2x plus c2 x e to the 2x plus c3 x squared e to the 2x. So there is our general solution for this differential equation. Now, that same process would happen. Suppose we had not a triple root, but we had a quadruple root. So this is kind of like an FYI. Suppose we had an auxiliary equation that would factor into m minus 6 to the 4th. So we would only get one root, which would be 6. So then our solution, since it's a 4th degree polynomial, you got to have 4 solutions. This would come from an order 4 differential equation. So the first solution would just be e to the 6x. The second solution would be x times e to the 6x. The third solution would be x squared e to the 6x. And then the fourth solution would be x cubed e to the 6x. So you can see kind of that pattern that's going on there by multiplying by an x every time. It's kind of an extension of what we talked about in section 4.2. We're not going to go through and prove that, but just to let you know, in case you encounter a differential equation that way, what that pattern looks like and how it happens. So if we look at another one, we have y to the 4th minus 2, it's not y to the 4th, it's the 4th derivative of y minus 2 times the 2nd derivative of y plus y is equal to 0. Take a minute and solve this one. This one is one you will be able to factor. So if you look at that auxiliary equation here, it's going to be m to the 4th minus 2m squared plus 1. This guy factors into m squared minus 1 times m squared plus 1. No, just kidding. Times m squared minus 1. And both of those are difference to squares. So you end up with 2 double roots. You end up with m is equal to negative 1 and m is equal to 1. They both have what's called a multiplicity of 2. Multiplicity is how many times that factor occurred. Okay, so what this means, if you were to graph this function, thinking back to 171, multiplicity of 2 means the graph is going to touch the x-axis at those values. So you could graph that and confirm that. So we found all 4 roots. We had to have 4. Since this is a 4th order differential equation, you got to have 4 solutions. So our y1 would be e to the negative x. y2, we could say, is x e to the negative x. y3 would be e to the x, and then y4 would be x e to the x. So then our solution is going to be using that superposition principle. So there's our final answer. So let's do one more. That's an initial value problem. This is a second order differential equation. And notice they have given us two initial conditions. So if we were to solve this, we would get m squared plus 1 is equal to 0. That's our auxiliary equation. That's where we always have to start. So that means m is going to be plus or minus I. So our solution is going to be y equals c1 e to the negative ix plus c2 e to the ix. And you can think about Euler's. So this is going to be c1 times cosine of negative x plus I sine of negative x plus c2 times cosine of x plus I sine of x. Using those even-odd properties again, we can put those cosine terms together. So this is going to be c3 cosine of x plus c4 sine of x. So now we're going to have to use some initial conditions. But the initial conditions are using y and the derivative of y. So we need to find the derivative of this guy. So the derivative of this guy, derivative of cosine is negative sine. Derivative of sine is cosine. Oops. So now we have enough information to substitute in So let's sub in that initial point. It says y of pi over 3 is equal to 0. So we're going to have 0 equals c3 cosine of pi over 3 plus c4 times sine of pi over 3. So we're going to get 1/2 c3 plus square root of 3 over 2 times c4. Those values are coming from that unit circle. And then if we substitute in y prime of pi over 3 is equal to 2, that's that second initial condition, we're going to have 2 is equal to negative c3 sine of pi over 3 plus c4 cosine of pi over 3. We know the sine and cosine of pi over 3. So check this out. We now have a system of equations we can solve. So with this one, we've got square roots in it. I'm not going to use a calculator to try to solve that. We want exact values, not decimal approximations. So let's try substitution or elimination. I'm going to actually use substitution. So I'm going to take this first equation here, since it's equal to 0, and I'm going to solve it for C3. So if I were to move that C4 term to the other side, and then multiply everything by 2, I now have a substitution that I can sub in for that C3. So I have 2 is equal to negative square root of 3 over 2 times negative square root of 3 times C4 plus 1/2 times C4. So this is going to give me 2 equals 3/2 C4 plus 1/2 C4. So that's 4/2 C4, which is 2 C4. So 1 is equal to C4. And now that we know what C4 is, we know what C3 is by plugging it in there. So then C3 must equal negative square root of 3. So then our final solution, this is finding the particular solution, is going to be y equals negative square root of 3. That's our C3 times cosine of x plus C4, which was 1, times sine of x. So in this case, because of those initial values, our constants ended up being real numbers, not complex numbers. But remember, real numbers are a subset of the complex numbers. So there's our solution for that one.